don't know if that's gonna happen somewhere, but it's fine. Okay, well, let's continue with the lectures by Subhroneel. And also today is an Indian festival, so that's why we have the Indian names. Thanks.
Yes, they will know.
That's why I started now. Yes.
So maybe it's the students know this dumplings later on because it's sweet. So what is the festival? It's
Diwali.
Diwali, so biggest festival, sort of in India. Okay, so let's start with the third lecture on the series. So for the past 2 weeks, we have been discussing this action. Right, and this, as we figured out, leads to equations of motions, which we recasted in forms like this, where remind you of this H's was defined this linear combination of P's and Q's, and R is whatever you get when you vary this L hat with respect to. So roughly speaking, this is the free part. It basically describes the kinetic term of two self-dual field-centered type variables. One of them is Hs, which is what we call unphysical. We are not interested in this one. The other one, Q, is interacting via some Lagrangian. And the only thing we demanded is that this Lagrangian is a function of Q and, of course, any other physical fields you might be interested in. Importantly, this cannot depend on P. And under this set of assumptions, we showed that this decoupling, which is very easy to see at the level of equation of motion, continues to hold true at the level of the Hamiltonian, which nicely decouples into Hamiltonian of some H plus, which describes a free chiral boson with the wrong kinetic term, and then this is a interacting chiral boson that we are interested in. This is the physical set. And so far, all of this discussion has been on a 4n plus 2 dimensional Minkowski space. Flat space. And today we want to generalize this whole construction, where this will be for 4n plus 2 dimensional Lorentzian signature, but some curved metric space time.
But then it will be a background, it will not be dynamical.
It could be dynamical, it could be background, both. If it, so once I finish the construction, what will happen is that if you, so I will do something to this, something akin to this. On top of that, if you add the Einstein invert, for example, then it becomes dynamical. If you choose not to add that, then it becomes a curved fixed background.
What I'm worried about is that this theory with the wrong kinetic sign, which nicely decoupled, when you put in gravity,
yeah,
it interacts.
Yeah, so that's the
then you're
absolutely
you're
yeah, that's the whole crux. That why we are dedicating a full lecture on this, because you cannot couple this thing straightforwardly to gravity. You have to do something clever. You have to do something quite new, because otherwise, as Ricard is mentioning, that this has the wrong sign kinetic term, and if this starts to gravitate, there's no way it's going to lead to a consistent field. So we have to find out a different way of doing it. And that's what we are going to do today. So for the last lecture, we did a lot of constraint system analysis and everything. We don't need all the details. I just want you to remember this fact, that as long as this thing does not depend on P, this decoupling holds at both classical and quantum level. Okay. So that's the lesson that is enough to remember from the last lecture. Okay. So, naively speaking, if you do the straightforward minimal coupling, you would replace the stars by star G's. The integration would be now integration over the volume form on the curved manifold and so on and so forth. And then you will not be able to avoid the fact that this non-physical field will now start to gravitate, and that's a problem. So our guiding principle should be, first and foremost, that H's cannot couple to gravity. So that's the first guiding principle, that whatever new formalism or new way of coupling to gravity we have to figure out, this is the first thing we have to ensure, that H's cannot couple to gravity. Now, we have actually already figured out a way where H's cannot couple to any of the physical sectors, which is what we discussed last time. That if you turn on a term like L hat and you don't do anything to the kind of standard kinetic terms, then this field does not interact with, for example, any of the other physical fields part. So this setup gives us a hint that we should think of coupling to gravity exactly like this, coupling to any other physical fields file. So we should introduce the coupling to gravity via a term like L hat and leave these two unchanged. It's a very strange thing to do. But if we do that, then at least one thing is ensured, that this thing will not couple to gravity at all. Okay? And this will have, of course, consequences, which we are slowly going to unravel. But is the premise clear? That think of coupling to gravity just like coupling to any other physical fields of interest. Which means, and for this lecture, the only physical field of interest we are going to be interested in is the metric of the gravity. So of course you can have turn on other fields, but that's not what we're interested in right now. So we want to turn on and in that. And roughly speaking, we are going to turn on an hat, which is going to look something like this. And I'm just going to explain what the symbols mean. This M cube, think of it as a linear map acting on Q's. So if you want big components, M cube would be something with 2n plus 1 indices, and it's given by some set of coefficients n, with indices mu1 to mu2 and 1, mu1 to mu2 and 1, and it's a contraction. So it's a bilinear in some sense to Q. Okay. This is the bare minimum that we could turn on. The reason being, if this is the only term through which we have coupled to gravity, and if you want to evaluate the stress tensor, you see, when we vary this action with respect to metric, the first two terms are going to be completely insensitive to the presence of metric because they don't know that the metric is there. This is the only term that knows the metric is there. And the stress tensor at the very least has to be quadratic in the fields. So at the very least, the kind of L hat you need to turn on is something like this. Okay. And this M is what we are going to now construct, which is going to now depend on the metric, the curved metric. And we are going to give an explicit construction of it. Okay. So now there is a potential caveat of confusing terminology. So let me set, and that terminologies are sort of used in a, not in a uniform way in the literature, sadly. So we have to fix on some terminology. So essentially what we have is that we have now some manifold, I don't want to call it M because I'm using M for this. So Okay, some sigma, some manifold sigma. And this has a non-flat metric G. Now defined on it. It's a Lorentzian signature metric, and that's defined on it. This is our physical manifold. This is my physical metric. But there is another metric that is now sort of playing a role, which is this typical flat metric. This is not to be thought of as a metric defined on this manifold. It's just some constant auxiliary kind of object. It cannot be promoted or should not be promoted to a field, where we have used this to define this kinetic term, as well as these integrals are being defined with respect to a form, volume form, that is corresponding to this eta. Because if you use the volume form corresponding to this, which you might be tempted to do, then this will start depending on the metric to the volume form, the square root G factor. So even there you cannot introduce that. And you already see this is very strange. These objects should not make any sense in a standard curve manifold with G. It should not have some nice transformation properties or anything like that. But what is important is that not this and this to have transformation, nice transformation property. What we want is that at the end of the day, all these three together should lead to something meaningful. So this might transform horribly, this might transform horribly, this might transform horribly, but if all the horrible things cancel them on each other and lead to something which is invariant and meaningful on this physical manifold, then we still have a sensible theory. And all at the cost of doing this is that so that we ensure that this guy does not couple together. This is a highly non-trivial statement, and without any justification or proof, it sounds like completely implausible. But we are slowly starting to see this thing later. So because we have two notions of metric, so to speak, even though one of them is metric, the other one is not, but it's still there. And there are things which transform as forms, as physical forms with respect to G, and then there is something which aptly transforms as forms if the physical metric was eta. So it would make sense to distinguish between these two forms, and I'm going to call them G form or eta form, and correspondingly, something could be G self-dual, which means the self-duality is now with respect to a Hodge dual with the metric G, which I'm going to denote by subscript G to the Hodge star. Or you have the eta self-dual, which I'm going to denote by just Hodge star. I'm not going to put the subscript. So if I don't have any subscript, that's the usual Hodge star that we have been dealing with in the flat space time for the last 2 weeks. Okay, and remember, we have the optional condition that Q equals to star Q. This is not to be promoted to be star GQ, because this whole derivation that this decoupling happens is done by assuming Q equals to star Q with respect to flat. Just because all of a sudden this phi is now the metric, we cannot change this definition, because then that proof will not go through. We'll have to try to rewrite this whole thing, and it may or may not work.
Sorry, I was taking a note while you were saying. So eta is the one which is inside the Hodge up there.
Yeah.
So can you write star eta there?
I can. I prefer not to.
Okay.
But like just star is always with respect to eta.
Okay, so star is the same as star eta.
Star. So star. So maybe I will just write it for once.
Yeah.
Star eta. I'm defining eta star. And whenever I'm using star with respect to the actual physical metric, I'm going to explicitly write the subscript G so that you know what I'm talking about. So once again, the field variables that appear naturally in action are these guys, what I'm calling eta forms, and some of them will have self-dual or anti-self-dual property with respect to star eta or just ordinary star. But eventually, what is going to be the physical variable is something that will have nice property with respect to G. and it should be self-dual with respect to this guy. Okay. So that's the whole idea. This is the terminology that I'm going to use for this. And I should tell you that this is not a terminology that is always used. Sometimes these are called pseudoforms, which is another thing because this is not like a differential form on the actual manifold. So it's called a pseudoform. But yeah, it's one terminology which I think makes it very precise what I'm talking about. So I guess I'll stick to this. Thanks. So how low should we go? Yeah. You can still see it. So okay. So now we want to construct this M and we want it to have, so okay, maybe at this point, I should tell you that at this point in the literature, as far as I'm aware, there are three separate constructions of M that has been given. So one is originally due to Sen himself. Then there was a construction that was given by Gabriel Lambert and Papageorgakis. And around the same time, there was a construction different given by Pichet. And they all sort of seem to differ in some sense, like how they are being constructed. But in all known cases where they have been explicitly constructed for non-trivial backgrounds, and they have been, so it has been constructed for circle compactification, torus compactification, K3 compactification, compactifications on arbitrary human surfaces, and so on and so forth. All of them actually sort of match. But as far as I know, there is no explicit proof that these three constructions are exactly always equivalent. So there are three inequivalent constructions could be, but they all give the same answers. So I'm going to follow the construction not by Sen, rather by Andriolo, Lambert, and Papageorgakis, which is first introduced in this paper. And there was a very significant extension of this construction by Chris Hall just last year. I think it's 748. So Hall's main result, I think we won't have time to discuss, but at some point I will mention that what is the generalization to this. But this is the thing that I'm going to discuss. But once again, in all known cases, the answers turn out to be the same. At least so far, there is no known example where they give different M. Okay. So we want M to have some properties. So we are going to construct M and we are going to postulate that M, we want this linear map M to have some properties. And these properties are very reasonable enough, but still we can motivate them. So one is that if Q is a self-dual eta form, then MQ is an anti-self-dual eta form. This makes sense because the way it enters the action is through a wedge product with Q. So anyway, its only anti-self-dual part is going to enter. So we might as well just postulate that we want M to be a map from self-dual to the anti-self-dual, but for eta forms. So forms which are supposed to be forms with respect to eta, or with respect to G. Okay. So M, once again, M is a map from the self-dual eta forms to anti-self-dual eta forms. It's a linear map, and we want this property. The second property is a kind of symmetry property. And symmetry property in the sense that if we have two self-dual eta forms, then this bilingual symmetric under the extent of Q1 and Q2. So this ensures that, I mean, okay, this explains that why I got a half in front of Q within Q. Okay. Okay, just with these two properties and the fact that L hat is up, so L hat is up Q within Q, this tells us the physical sector of the equation of motion. So for example, this R is going to be just LQ, and I'm going to vary this with respect to Q, right? It's going to give me LQ, but because of the symmetry factor, there will be two such factors, so that cancels the half. So the physical sector equation of motion, remember, which was d of Q minus R equals to 0, now translates to d of Q minus m of Q equals to 0.
Is there any reason why we get a minus for just m?
Yeah, because the Lagrangian it elevates Q with M, Q and Q is self-dual.
Right.
So it's only the anti-self-dual part of it which enters the action. So we are saying that, and that's the only where M is entered in our discussion. So we might as well sort of, postulate it to be anti-self-dual from the very beginning, because the self-dual part is never going to be
Okay, so right.
right. So it's
It's more like an assumption.
yeah, these are, if you want, these are sort of properties which I'm going to sort of
I was reading like if this then that, but it should be written as if this and that.
So this is the definition.
Yeah.
If we have a self-dual form, then we are defining it.
And so you would define it with the opposite sign if we have an anti-self-dual form.
Yes, if this is an anti-self-dual thing, if this whole discussion was the dynamics of an anti-self-dual thing, I would have defined it himself. Okay, so just to remind you, what would be the equation of motion that you would expect of a self-dual field strength on a curved manifold in the standard textbook way of doing things, like in pseudo action way of doing things, right? So in the pseudo action way of doing things, you would have a say Lagrangian, which would be somehow DC will start DC, right? And then you would an action, and you would vary the action with respect to this, and then on this you would impose the self-duality condition, and this would basically tell you that the equation of motion that you should expect is some self-dual field strength
Just one clarification.
Sure.
M takes self-dual eta forms to anti-self-dual eta forms, not any eta forms to explicitly anti-dual eta forms.
Yeah, not yet.
Okay. Oh, not yet, or okay.
Not yet. Eventually, we would want to extend its action to all eta forms, but not. I have not defined it how to do it so far.
Okay.
The way we have defined it is a map from only the self-dual eta forms to anti-self-dual eta forms. Right, so this is the equation of motion that we would expect for a free. I mean, free in the sense that it only interacts with the gravity. Self-dual field strength and a curved manifold. Right, this is what you would get in the standard supergravity if you were to turn off the Chern-Simons terms, for example. So now the equation of motion that we have is d of q minus m equals to 0, which is awfully close to this. If somehow this combination has the interpretation, at least functional, of a G self-dual form. So we can make a connection between the equation of motion that we have derived from sense formalism and the equation of motion that we derived from the pseudo-action formalism. If you say that this M has the property such that even though Q is an eta form and NQ is an eta form, this combination Q minus NQ, I'm going to call H subscript G. This is a, okay, first and foremost, this is a G form. And more importantly, this is a G self-dual. So these are all reasonable properties that you should expect out of M if the formalism has to work. The first one is simply saying that since you are introducing M through this combination Q with MQ, just might as well think of this as an anti-self-dual thing. The second is just simply saying that you can always choose M such that it's symmetric under the this bilinear is always symmetric in the two arguments. And third one is saying that how to make connection on shell to the actual physical form on the manifold on which we are interested, right? And then it says that this particular linear combination should have an interpretation of a G form and it should be self-dual with respect to the actual physical metric. If we can construct an M which satisfies all of this, then this procedure is going to work through. So we are going to construct an M which has to satisfy these properties. Okay. And then there is a fourth and final property that we should reasonably expect is that in a special case, when your physical metric is actually the flat space metric, then you want this M to be identically zero. Because when our physical metric was really the flat space metric, we didn't need any of this, right? We were doing perfectly fine. So you should not really need to introduce a Q as MQ term. So this MQ should have the property that whenever you put the metric with the flat space metric, it should identically just collapse to zero. Okay. So these are some sort of axioms or assumptions, so to speak. And given this, there are two big questions we have to answer. One is that does such an M exist? And if yes, how to construct it? That's the first thing. Right? Because I have not yet shown you, I have not yet established that such an M will exist. We are just only saying that for this formalism to make sense, we are just following the flow of logic that H's cannot gravitate. If it cannot gravitate, then the only way to introduce coupling to gravity is through an L hat. At the bare minimum, it has to be some sort of bilinear. And that bilinear, if it has these reasonable properties, then we can make a connection to the, at least on shell, we can make a connection to the known physics of the self-dual forms in the curved manifolds. But the question is that does such an M exist? And if it exists, how do I construct it explicitly? Right? Because it's not enough to say that it exists. We want to do computations with it. So we need to know explicitly. Somebody gives me what is the curved metric, I should be explicitly be able to construct it. So that's the one. And the two, notice that we now have this weird possibility that you might still insist on thinking of this P and Q as differential forms on the curved manifold. Because you say that okay, these are indexed objects, right? These are some 2L and 2L plus 1 indices respectively, completely antisymmetric. Why can't I think of them as differential forms? Well, you can, because at this point we are just constructing the whole framework. You can assume that, but if you do, the first two terms are going to badly violate general coordinate invariance. And there is simply no way of making sense of it. Because you're integrating proper differential forms on a curved manifold with a completely wrong measurement. And that's not a good thing to do. The second possibility is that you abandon that thing and you say that PQ have novel transformation properties under diffeomorphisms. Diffeomorphism is less than meaningful, such that the total action is diffeomorphism invariant? Because that's the only thing that would make sense. You don't want to violate diffeomorphism invariance of a gravity theory. Then the only possibility is that P and Q are some sort of weird object which are going to have some sort of new transformation rules under diffeomorphism, such that this whole thing is diffeomorphism invariant. Then the question is that what are these normal transformations? What are they? So it's not enough to construct an M which makes this connection. You then have to figure out what are the transformation properties of P and Q, and then establish explicitly that this thing is still invariant under general coordinate transformation. So these are the two big questions that we have to answer. Okay. Any question at this point? Because if not, then we are going to first explicitly construct M. Of course, the question answer to both of these are yes, otherwise we are not going to have this discussion. So first we are going to give a construction for this M and show that it has all this sort of properties that you would expect out of it. And then we're going to figure out how should P and Q transform such that this whole thing is diffeomorphism invariant. Okay. Okay. So we want to construct this map M, and since I'm following Andriolo Lambert Papageorgakis, it turns out that it's simpler if we modify this property 1 a bit, in the sense that, like Vasu was asking, extend its scope of action from just the self-dual interforms to the space of all interforms. And the extension is somewhat trivial. So let me call it 1 star, which is that if this is self-dual, then this maps to an anti-self-dual thing. If there is a anti-self-dual thing, anti-self-dual interform, then M's action on this is 0.
You didn't really change anything.
I didn't really change anything. It's just a trivial extension. But now the definition of M is from eta forms to eta forms. So it's just I've increased the domain of its definition. That's the thing. But as far as the physics goes, I have not really changed anything. That's why I said it's like a trivial extension of this. Okay.
I mean, why the question becomes, why did you not do it in this way from the beginning?
Yeah, I mean, you can ask that, but then in some sense you can say that I didn't need to, right? It's fine to just sort of define a map which has restricted domain, and that should really do the trick. So this whole thing is that in some sense, if you extend it this trivially, then an expression is easier to find. But then eventually the meat of that expression is in the part which I already mentioned earlier. It's just for technical reasons, so to speak. So now with this extension, you can actually make this property explicit if you replace everywhere M by this, where the projectors P plus minus are the usual thing.
Plus minus.
Right, so this makes sure that even for an arbitrary form, this one will force it to become self-dual, and the name will map it to an anti-self-dual thing, right? And then this sort of ensures that even if by chance you had something self-dual surviving, it would just kill it off. Now, one of the things that we have to demand is this third property, that this combination Q minus MQ must have an interpretation of a G form, and more importantly, a self-dual G form, the G self-dual form. This, or maybe what I can do is that I can just bring everything on one side. Is equals to 0. That's going to make our life easier. And then essentially, we want to replace the M by this. And remember, Q, you can always replace Q by P plus Q, which is a trivial thing to do, right? Because Q is self-dual, it's just inserting an identity, so to speak. So then you have 1 minus star G, P plus Q, and 1 minus star G. The M I'm going to replace by, as I said, N minus plus equals to 0. And I can sort of write this thing as a operator equation acting on Q on both sides. So we can just forget about Q in this one.
So how did you get the 1 minus star G in the second term?
So this one.
No, the second one. Yeah.
Oh, I just broke this out. Sorry, this was full. Q minus MQ should be self-dual. So 1 minus star G should kill it.
Okay.
So then I break it into 2 terms, and then I just rearrange. So this one is of course true when acting on Q on both sides. Remember, M, whenever I'm writing in here, there is actually a name of Q here. In this one, the Q is not there. It's really an operator equation. So think of it as like a operator equation for some linear operator acting on the space of eta forms.
Well, so in the equation above, should there really be a Q there?
Yes. So M here, I
Yeah.
should think of it as M because of just this.
So then I don't writing P. Yeah, I don't see the P plus there.
Oh, sorry. You should write the Q here.
Yeah, okay.
That's right. Because I'm replacing the whole operator with this new one. Now the first step in ALP's construction is to, so you basically sort of make use of a basis for eta self-dual forms. In fact, we would need eta self-dual and eta anti-self-dual. So let me call them omega plus A, omega minus A. I'm following exactly the notation of the paper so that it's easier to compare. And this A is something that runs over all the different numbers of anti-self-dual or self-dual forms that you can have in 4n plus 2 dimensions. Is this something clear to everyone? So if you just have a 2n plus 1 form in 4n plus 2 dimension, the basis dimension of the vector space is 4n plus 2 times 2 plus 1. And the self-dual and anti-self-dual is precisely half of that. They are both equal, and it's precisely half of that. That's fine. And of course, both of them are going to have the same range. It's only the placement of the indices which are going to distinguish sort of which one, and of course this notation plus and minus is going to distinguish that which is the basis for the self-dual eta forms and which is the basis for the anti-self-dual eta forms. Okay, so this is the self-dual one, right? If it's not clear, star of this is star of this, and this is the anti-self-dual. Star of this is minus star of this. Okay. What this tells us is that M can now be represented by a matrix. So M, when it acts on an anti-self-dual field, is 0 by definition. But when it acts on the self-dual field, this we can denote. And when it acts on a self-dual thing, this becomes an anti-self-dual form. So it will be some MAB omega minus B. So construction of this M now reduces to finding this matrix MM in this basis. Yeah. So we have just chosen a basis, which is a basis for the eta self-dual and eta anti-self-dual forms. And in terms of that basis, the linear operator M can be encapsulated by a matrix MM.
Yes, I would write the indices in the observer like that. That's really not doing it.
Yeah.
I'm
Is,
thinking
there-
out loud.
is there any reason for that? Exactly. So will there be a symmetry of M? Will
So-
MAB be a symmetric or something magic?
Yes, that's because of the property 2.
Mhm.
The
Okay.
that
Yeah, so
property
then
2
it makes sense.
Then property 2 would force us that this matrix, it may be, has to be the same as the B. So once I have chosen the basis, this one is basically the property 1, right? And this one is a consequence of property 2. And I could also mention that I want this basis to be sort of orthonormal. So they have this structure.
We start with 0.
Sorry, we start with 0 and this is 4 and plus 1. And because it's Lorentzian, so we should just keep things specific. And the 2 is a normalization that I choose. So it probably makes sense. So okay, I should mention one thing, that these notations are following ALP, but the action they have a slightly different normalization for Ashoke. But since for the last 2 I've been following his notation, so it's kind of like a little mixture of notation. But this 2 is harmless. I mean, what's really important is the delta function. Okay, so now what we want to do is that we want to recast this operator equation in terms of this basis and think of it like what is the consequence for MAB? What does the property mean for this MAB? Now, this one is trivially true when it is acting on anything which is omega minus A. Because both of them has E plus on the rightmost sector. Right? So it's trivially going to get killed. So this operator equation is not going to give us anything significant or anything sort of substantial when it's acting on omega minus A. But when it acts on omega plus A, we have, so let me call this equation something. Let's say equation 1. So equation 1 acting on omega plus A gives us essentially So this one is just simply going to give me 1 minus star G omega plus N, right? Because P plus acting on omega plus is just omega plus. And this other one, this thing acting on omega plus is going to give me this omega plus. This M acting on it is going to give me MAB omega minus B. Omega minus B when P minus hits on it gives me back omega minus. And 1 minus star G is there on both sides. And bring everything into one side. And that's the equation. Is this okay? Or is it too fast? No, it's okay. And what this is telling us is that in this basis, this particular linear combination has to be G circular. Right? So this whole combination is G circular. And this is really just a consequence of eventually the property 3. Because remember, property 3 started this whole thing. So it's just demanding the property 3 has now been casted into the language of that basis. Okay. Now, oh. I don't want to use this thing, so let me get this. Okay. Now the next step is to construct another basis. But now you construct a basis for G circular forms. You can also construct it for G anticircular forms, but since the dynamics is not going to give us any G anticircular things, it's not going to be of interest to us. And let's call that curly phi of A. And the A and alpha are the same indices, right? Because the combinatorics has not changed. Right? Because this is only sensitive to the dimension of the manifold. Doesn't matter what metric you use. Now, here is the sort of crucial thing. On the physical manifold, I call it sigma, at any given point P, you can choose a local neighborhood, some say U around P. And in that local neighborhood, I should be able to express this basis as some sort of linear combination of omega plus and omega minus. So the claim is that I should be able to find some matrices which are going to call M and K such that locally I should be able to find N and K such that phi A is given by this linear combination. Right? It's not a controversial statement. Everybody agrees on this one. Now, since omega plus A minus NAB omega minus B, this combination, we showed that property demands that it is G circular. Then I should be able to express this in terms of this basis. So there should be some matrices capital theta such that it is true. And I'm just going to replace phi by this expression now. So we have, so you can bring everything on one side. And we call that omega plus and omega minus separately form basis for two different vector spaces. Which means that their coefficients has to be individually zero, right? And this gives us the inverse. And once you use that, it will be by MA. It's quite straightforward to see, right? That like this combination has to be identity. So theta is inverse. And if you put it is inverse, then this combination has to be here with a negative sign because there is a negative sign here. So that's what it's there.
So your M will only be defined locally.
So far, this construction is completely local at any given point. So this is something that is a feature of this ALP construction. The construction that Sen gives, for example, doesn't require this. It can be, it's an expression directly given in terms of real lines. So then that's an expression that is pretty much valid everywhere. But then the generalization that Hull did for this, so there are certain aspects that he generalized, but essentially the crux of the argument is that you should be able to find this N inverse everywhere and sort of glue it together and find a well-defined invertible matrix N everywhere. As long as the orientation that is defined by star eta and the orientation that is defined by star G are the same. Which makes sense. Because if the orientations were different, then of course at some point this should break down. Otherwise, you can always locally construct this, glue it all together, things work. There's an important generalization that Hull did as well, which I'm going to discuss later. For now, let's stick with this. Okay, so in some sense, we are done. This is the construction of M, right? And you might sort of worry that, where did the geometric information went in? Well, the geometric information went in precisely trying to construct the basis phi's and the omega plus minus. When we discuss an explicit computation, we can see that. But for example, already I can sort of give you a highlight. So suppose, let's take a very simple example. Now suppose you're in 2D, right? In 2D, you're interested in one forms, which can be self-dual or anti-self-dual. So the basis of one forms are dx0 and dx1. And eta self-dual and eta anti-self-dual forms are going to be this combination. So this is your analog of omega. But now if you have a non-trivial metric on the manifold, then essentially your phi's, this should not be just dx1, but it should be star g dx0, which is dx1, but then it's going to have some factor because g is non-trivial. Because the epsilon will have a square root g factor sitting in there. And if you want the other anti-self-dual one, let's call it phi minus a, it should be the other one. So if you know the metric, the common metric, then you see that the information goes in here. And then once you've constructed this and you want to express this in linear combinations of omega plus and omega minus, you see the metric components are going to sort of sit in the same and the case. And that's how M is going to know about what metric is there.
If you try to do it in terms of the field lines.
You can do it in terms of the real lines as well.
So the difference is just some overall factor.
So in terms of the real lines, okay, I mean, this whole thing you can recast in terms of real lines, then there is of course no difference. What Ashok did is that he sort of found M a little differently. His way of finding M is essentially by comparing directly like what equation of motion you get from his formalism and what equation motion you would expect for a curved self-dual, on a curved manifold, what is a self-dual thing. And he could sort of from there directly sort of give a construction of M in terms of the real lines directly, which seems to work in that way. And then you don't have to go through all this, but then that expression is sort of a handful. Like it's a very big and complicated expression in terms of real lines, whereas this is computationally much simpler. Because this is one of the simplest thing to compute, and very directly you can read off the matrices NK and then immediately you have this.
But if you use the field lines here and express dualities of duality in the time space basis in the
Yeah, you can do that. Absolutely.
Then everything seems rather simple.
Everything is very simple. I mean, this construction is completely amenable if you don't want to use the metric and you want to work in terms of the elements. It's perfectly fine. That will also work. Absolutely. It's completely a matter of taste at this point. If someone is more comfortable working with real lines, you can easily express all of this in terms of real lines and find the matrices that way. If someone is more comfortable working with the metric, you can also work with that, and etc.
Because the M and K seem rather abstract. But if I use field lines, I could just write them down in terms of field lines, I guess.
Yeah, you could, but then my point is that that is essentially the same thing that I would get by constructing N and K using this way and then expressing it in terms of real lines.
Right.
So it's not going to give me any different answer.
Right.
It's just two ways of computing.
I'm hoping it seems like simpler.
Yeah, of course. I mean, as I said, I mean it's a matter of comfort. Like if you're more comfortable working with real lines, you can do that. And so.
Yeah, it's just that geometrically it looks more ugly because this one relies on that you're choosing a point, and there you can make the identification between eta and g and so on. And this only works in a neighborhood by the inverse function theorem. So to make sure that n is invertible, and then you have to do.
Yeah. So the whole thing is that. Okay, maybe instead of sort of keeping it for later since the questions are arising, let me tell you what generalization Hull did. What Hull did is that he showed that this whole construction walks through, even if you change these metric, sorry, I removed the action somewhere, but even if instead of having eta self-dual forms, so the reference fixed metric eta, you change it to any arbitrary curved metric G bar. So there is nothing special about eta. This is still not the physical metric, but it can be some arbitrary curved metric G bar. And then what Hull proves is that as long as G bar and G are off by something which is quite small, you can add the orientation defined by G and G bar on the end. You can always use it.
Yeah, deformation.
Yeah.
Yeah.
Which I think very nicely puts a end to this confusion that whether I can find inverse. But yes, there was a time from like because you can see that there's a 3-year gap between the two papers. There was a time when it was not clear that this construction by ALP should walk through. It seemed to walk through in all the compactifications that you would normally do to test supergravities and stuff like that. But of course, for arbitrary manifolds, it was not clear. But I think once Hull's paper came out last year, it became quite clear. Because this G bar is completely up to us to choose what we want. And you can always choose it to be something which is a little different from the physical metric. And then you can always input this.
Does something interesting happen if technically the same?
Yes. So if you do take them to be the same, one of the interesting thing that happens is that you don't, so this n equals to 0 condition now becomes there important in some sense. But then there is the classical theory, there is sort of no problem. But then there is a problem that it comes in the quantum theory. Because in the quantum theory, I would want to do a path integral over G, but not path integral over G bar. But now how do I distinguish? Because it's coupling to the same metric. And then my guess is that theory probably going to make sense classically, but quantum mechanically it won't be a well-defined thing anymore. Because there is no way. So okay, I should also say that there is a recent paper this year which showed that the separation that we proved last lecture, right? I worked with the eta thing, but it also works if you just replace eta by some fixed G bar metric. Okay, so Hamiltonian still factorize this, everything works. But then the point is that if you make it G, then in some sense, it's coupling to the same metric. So that won't be a good thing, because that would be the thing that we are trying to avoid. Because essentially what happens after you replace eta by G bar is essentially you have two sectors where HS couples to G bar and the physical HG couples to G, and these two sectors don't talk to each other. But if you make G and G bar same, then how do you distinguish? Like, what is the label that will distinguish that, oh, this metric is same, but it's not really the same? I mean,
well, one is sort of fixed, like a background or something, and the other one is dynamic.
yeah, but I mean, if it's the same, then how do I distinguish them in the path integral, for example?
Then you follow something.
Yeah. Or, I mean, okay, one thing is that you can give them some internal level, but then now we are into sort of weird physics trajectory, I mean, territory. What's an internal level of a metric, right? Okay. Okay, I just wanted to say one more thing, is that in the spatial case, when you have G to be really the intermediate, then you see the basis phi is going to be the same as omega plus. They might be off by some linear combination. But self-dual with respect to G and self-dual with respect to eta are not the same thing. Which means that this matrix has to be exactly 0. And if this vanishes, then you see the ring vanishes. Which means that in this construction, this property is identically true. We didn't have to impose it separately. So we made use of this, Right. We made use of this, This is identically true. So far, we have not made use of the fact that A may be symmetric.
When you mentioned it.
I mentioned that it should be something symmetric. So now either this guy is symmetric or it's not. If it's not, then we have to do something extra. But then, as it turns out that this guy is symmetric, so we can quickly see how it goes. So let's take 2 copies of this equation. So I'm just copying this here. So let's take 2 copies of this, and since both of them, so we take 2 of these forms, one and another one the same thing, and we want to take wedge product of them. Now both of them are self-dual with respect to star G. So the wedge product should vanish, right? That implies in terms of this. Right? It's just this wedge product itself has to vanish. And if you use the fact that omega plus and omega minus, they themselves were delta function normalized up there on the top. So this is it clear that I am writing this, but what I mean is that this copy and this copy. I'm just not writing it because of the space constraint. It's just 4 factors. And if I multiply them out, then only the omega plus and omega minus are the terms I should pick up. Because omega plus wedge, omega plus, and omega minus wedge, omega minus are going to vanish. Because they are also self-dual and anti-self-dual, but with respect to a eta. But for cancellation, it doesn't matter which or it's self-dual with respect to what. Right? And then essentially I'm going to pick up 2 terms. Delta is 0. This is delta CB. This is delta AB. And this gives me A.
You don't have any contributions from the big theta term?
The big theta is precisely an inverse, right? So, okay, I mean, what I really want to multiply is these 2 copies. Since I don't have space, I'm just simply sort of quickly arguing that why this is 0 because you have both phi's.
Oh, so the thing after the bracket is equal sign, not the minus.
No.
Oh, okay. Yeah. Well, then, yes.
I'm really multiplying 2 copies of this here. That's what I'm after. But since I didn't have space, I just use this right one. Right? This one vanishes simply because it's a wedge product of 2 phi's, and both of them are G self-dual, so they're 0. But then secretly, these are like linear combinations of omega plus and omega minus, specific linear combination. If I take wedge product of that, expanded it out, then these are the only 2 terms which are going to survive. Everything else is sort of there, and then I use the normality, and then it simply becomes the antisymmetric part of MAB is 0, which is otherwise MAB symmetric. So we are given a construction of M, which has made use and satisfied all of these properties. Right? Now, let me just make a couple of observations before we move on to discuss the different morphisms.
Side. Omega plus minus, there are 2 and plus 1 forms.
Sorry,
2 omega plus and omega minus are 2 and plus 1 form.
2 n plus 1 forms, yeah. Self-dual and anti-self-dual.
When I switch sides,
Mm-hmm.
I have to
Yeah, you'll pick up a sign.
pick up a. Oh, that's why.
That's why I
Yeah, you have minus.
Yeah.
Yeah, okay.
Yeah.
Good.
So a couple of more. Some observations if you like. Because I personally find this quite fascinating that you have this very new and non-trivial way of coupling to gravity, but somehow still things seems to make sense. Especially in terms of that you're using variables or using sort of field variables which are very non-standard. They have nice transformation means under a completely different thing, which is not the physical metric. And yet somehow at the end of the day, it kind of makes sense. So first thing is that we can formalize these things a bit more. So first thing is that note that on the eta self-dual forms, M acting twice on any eta form is going to be 0. Because whatever omega is, A omega is going to make it anti-self-dual. And we have defined that A acting on anti-self-dual is 0. So it's like an important operation on the space of eta forms. Which means if you define a map, then we can small n, which takes an eta form omega, is specific linear combination. And remember that this linear combination, so okay, if this is eta self-dual, then this linear combination is supposed to be G self-dual. So this small n is a map from self-dual eta forms to self-dual G forms. And this is the guy which is going to do sort of a lot of heavy lifting. Because you are going to express everything in terms of these guys. And at the end of the day, somehow this guy should make an appearance and give you back the actual physical quantity which is of interest to you. But if this is the map, then its inverse map is going to be simply this guy. Is this clear?
Because of nilpotency.
Sorry?
Because of nilpotency.
Yeah, because of the nilpotency. So we can quickly check that. So let's say we inverse acting on M of omega. So M of omega is omega minus capital A of omega. And M inverse. So I'm just using this definition for M of omega. Now I'm going to use this definition. It's going to give me omega. So first of all, this linear map with this steps. Every person is going to give me omega plus M omega. This is going to give me minus M omega minus M of M omega. This guy is 0. These two cancels.
But it's defined not on all forms. Yeah, is it, or?
No, it's really a map which sort of. So I'm using the same notation, but I mean you have to sort of implicitly understand that the domain of M inverse is the G self-dual forms and the target is the eta self-dual form and vice versa for the M. Okay. I mean, you should remember that M is not, it doesn't take an arbitrary eta form and makes it G self-dual. It only takes eta self-dual and makes it G self-dual because we did not demand this property for an arbitrary. So this property 3 works for Q equals to star Q. I did not demand that Q is any eta form and then that combination has to be this. That's a too strong a demand.
So it's slightly misleading when you write the inverse map omega. Omega.
Yeah,
a different symbol.
Yeah, I should probably use a different symbol. I'm being a little lazy here. So let's say. Okay. Okay, but then what this means is that if you are given any G self-dual form, some F G which is star G, then you should be able to write it like this. And there is some eta form F which I'm making it self-dual by acting V plus in front of it. So there is some self-dual eta form which under this small n map gets to the center. So this is the mathematical structure. That's how it's working. Like we want to write down the action in terms of these guys. But at the end of the day, you want the physics of these guys. And then the mapping which takes you for this is precisely this map model. And of course, explicitly this is this. But now you see, if I act with a P plus on both sides, because remember P plus is something which is the projection for the etas, not for G's. That's important because otherwise this is medium on G's. This one is P plus squared if you do P plus as a projection. You do it twice, once, doesn't matter. So this one remains P plus. This one, M always makes it anti-circular. So P plus is going to kill it. So that's the answer. P plus F is P plus FG. Or, in other words, P plus F, I can explicitly write it as star of FG. So this is true for any cell G form and given such a form, such a map small m. In our case, the thing that we have been discussing so far, our P plus F is what we were calling Q. Right? Q is star Q, some cell dual thing. And Fg that we are eventually interested in is the physical cellular form Hg. And this is simply telling us that Q is 1 plus Hg. Why is this equation interesting? It's telling us two very crucial things. One is that the degrees of freedom that is included in the physical field of interest is the same degree of freedom that is already sitting in the Q. It's just that Q doesn't have nice transformation properties that we would expect out of a differential form. But then again, it's also telling us that if this has a nice transformation property, which it does, because it has the interpretation of a form on a manifold, then this is the thing that is basically spoiling the party. This is basically telling us that Q cannot have standard diffeomorphism invariance, because this is not a well-defined object on a manifold with a matrix. Okay. So if you want H to have the standard diffeomorphism properties, which you would want that, of course, then you are forced to consider Q to have non-standard diffeomorphism. You don't have a choice.
And if you hit it with minus instead, then we would get m times Q, so you could somehow.
Yeah, exactly. The M information is sort of sitting in the 1 minus star part of the FG. And in fact, you can do something better if. But if you want, you can sort of invert this, right? You can express Hg as sort of something related to Q, which is essentially, remember that put phi upstairs. But this phi is sort of precisely the combination up to this A inverse omega. Or maybe put it this way. Let me do it here. I think it's not something simpler. So HD, you can think of the rest. This is just a identity. I'm just writing H equals to H because this is Hg. It's supposed to be self-dual. Then if you are hitting it with the G projector, then that's essentially what it is. But then if we expand Q as QA omega plus A, then essentially, let me just give you the final answer of this. Equal. And this is what each is in terms of the components Q. This makes it very manifest that it's a self-dual form because it's written in terms of that basis only. And it also makes it manifest that it's the same degrees of freedom encoded in Q whose linear computation is appearing in H. So you can go both ways. You can express Q in terms of Hg and Hg in terms of Q. Okay. So this is the sort of observation, like because it's quite obvious that it's something a little strange and something unusual is going on. But we are not losing any degrees of freedom, we are not introducing any degrees of freedom. We are using some sort of unusual variables, but with some specified mathematical properties such that at the end of the day we recover the physical variables which we are interested in. But because we cannot nicely express our Lagrangian in terms of this variable itself, if we could, then we didn't have to worry about all this PQ business. It means that we need to sort of check the diffeomorphism properties explicitly and figure out that what diffeomorphism property should be attributed to Q's and P's. And you realize that Q and P is not going to be something that is going to be completely arbitrary diffeomorphism properties because it's pretty much fixed. Because if Q is expressed in terms of this combination, I can just the right hand side I can do a diffeomorphism transform. We can figure out what it is. And for the P's, the basic principle is going to come from the fact that H's cannot gravitate. And all of it should be tied together by demanding that the total action is invariant on the diffeomorphism. And that will help us in fixing all the non-standard diffeomorphism properties and establishing that this combination is diffeomorphism invariant. So that's what we'll discuss now. But if there is any question concerning the construction of A, this is a good point to ask. I guess not. Let's move on. So, diffeomorphisms. Our logic is first is the total action must be diffeomorphism invariant. So, just to remind you, this was our action. And all of these integrals are not integral over the manifold. These are integrals with respect to sort of thinking of eta as the giving the volume form. So in some sense, none of these integral together kind of makes sense on a manifold with metric G. The hope is somehow, so in fact, perhaps the more rigorous way of writing this would be that this is meaningful. So this is an integral over some sort of Minkowski manifold, but the hope is that somehow this would be written as some integral L hat, which is integrated over the physical manifold with the correct volume form and so on and so forth. So we are not interested in finding an expression for L tilde because this will be very if we could find a simple expression, there is no need for doing any of this. That's not the point. But instead, what we are going to argue is that this whole thing together is going to be diffeomorphism invariant. So if I just read any of these terms, they are individually not, either together. So the rigorous thing is essentially writing them under the same integral sign. Now, if I take a variation, so I'm just taking a variation, diffeomorphism variation of the total action. My goal is to figure out what is delta xi p and delta xi q, such that this whole thing is invariant, right? And this is just a normal variation thing. Like this is the only term from the first one. The second one has two terms when delta xi p hits p or q, and the last one will have a contribution when the q is transformed. But remember, m is something that is going to be a transformation, function of the metric. So diffeomorphism is going to act on the map m itself. So that's the last contribution. Okay. Now the first thing I want you to do is just focus on the first two terms. Just focus on these two terms. We will handle the rest later on, but first just focus on these two. And I can write it. So I'm just focusing on this. I can write this thing as BP. So I think there should be an overall sign. We'll just I'm taking this, so this should be there, and yeah, and this is the correct sign. Now on this term, we can add and subtract I added and subtract the term which is dp with b of delta xi p. I can do that. And then I can forget about this because it's a total derivative. Right? Forget about it. And this, if you remember our definition of Hs, is nothing but delta xi of Hs, because Hs was dp plus star dp minus q. So this term is telling us this is dp, which delta xi, which is just the first two terms, up to a total derivative, total boundary term which we are dropping. Remember that Hs was dp starting minus Q. It is what the unphysical field. And it is the field we do not want to gravitate. If we do not want it to gravitate, the simplest transformation rule that you can attribute to it is that you say that it doesn't transform. It's invariant under diffeomorphism. Which is a weird statement because remember this thing has indices. Right? It has 2n plus 1 number of indices. We are saying that this is an object with 2n plus 1 indices, but it does not transform under diffeomorphism. And it's a sensible thing, right? Because if you don't want something to gravitate, don't make it transform under diffeomorphism. As simple as that. So we postulate delta psi of H is zero. And the moment you postulate this, this means that the variation of the P and the variation of Q are no longer independent. They have to conspire in such a way such that this combination is always invariant under diffeomorphism. And that essentially boils down to the fact so this the answer. Because dp plus tau dp is nothing but twice of this tau dp plus dp. And I just took a variation, took q to the other side, and that's the equation. Is it clear? I just took a delta psi of this on the both side. This is this term minus delta psi of q equals to 0. I took the delta psi q on the other side. That's this. Okay. So now remember we do not have the freedom to independently postulate delta psi p, delta psi q anymore. If we determine one of them, automatically the other one gets determined. Okay, so that means the variation of the action, you can forget about this first two terms.
Well, it's not quite because of the projection that there could be some non-zero.
Yes, of course.
B, which will not.
Yeah, the P minus component of delta psi p is not fixed. Yeah, that's true. But for example, if somehow I fix delta psi p, then delta psi q is automatically fixed. So that's what is going to happen. So. Okay, now this analysis has convinced us that we can forget about the first two terms because that is essentially proportional to the variation of this unphysical field under diffeomorphism, which is reasonable to postulate that that should vanish or that should be invariant under diffeomorphism. So we can forget about this two and just focus on the last three. Okay, so is it okay if I just erase this?
Do we need to?
We don't need to. Okay. Okay, then I will look at it. Let's keep it. It's fine. So okay, maybe then I just switch the boards. I want to focus on now on the last three terms. So we have established that delta psi of this boils down to this. This and finally the relation of the n. So this is what I'm still using the joke. This is what we have boiled down to. We are going to simplify this a bit. First and foremost, we are going to make use of the fact that delta psi q is that. Because we have already used that to set something to 0. So it makes sense to replace this. So this term becomes I just replace delta z q by 2p plus b delta z. Now on this 2p plus is redundant because this mq is anyway anti-cellular. So it's anyway going to talk only to the cellular part of this, so we can forget about this 2p plus. And then this becomes
How about the two?
the 2 is there because okay, our normalization in the sense
I
is
think, like, I was putting out for like over there's a half.
There should be a half for Q, which and Q.
Like,
Last but one.
last two terms are the same, right?
There should be a, yeah, that should have a half.
no, but you
The
see that delta psi is going to heat on both values
Yeah.
and it's symmetric. So that kills off the okay. So Q which MQ you should really think of this is one.
Okay.
Right.
Yeah, okay.
But in the same vein, then I guess you should put a parenthesis in the last term, in the fifth term, around the delta of m.
This is the map that is acting on.
Okay. Okay.
But what about the two? Why didn't you know?
Yeah, the thing about the 2 is that the normalization that kind of works out is that the cellular and the anti-cellular comes with a factor of 2.
I mean, the
So,
projection
sure.
operator is with a half, so that p squared is p.
Yeah,
But now you say that you project it on the circular part, so I would say p plus on this is just this. And the 2 is left.
yeah, but the normalization that we are working on is kind of like this, that if you have dp plus star dp and dp minus, sorry, d some p minus star dp, then this thing is sort of normalized to 1. The wedge product normalization has this sort of extra 2 factors. Remember in the delta function, for example, this omega plus omega wedge omega minus, I have this 2 delta AB, not delta AB. So that's the absorption of 2.
Okay. I believe you.
So yeah, it's just me trying to compromise between one notation of writing action and then another notation of doing the. So this normalization sadly is a bit off, but
Okay.
there's nothing that goes wrong if you just change normalization and keep factor of everything correctly. Okay, so yeah, I didn't do anything with the other ones yet. I just talked about what happened in this ones. And now what we can do is that we can sort of remember that just our HS was that our HG was defined to be this combination, Q minus NK. And this we can write it like this. Right, the negative sign makes this thing P wedge Q, and then the negative of negative becomes this plus Q wedge MQ, right? And then of course you have this other term. But here I can replace Q by Q minus NQ without changing anything because M with this is still going to vanish. Because if M is anticellular, delta psi of M is also anticellular. So I can write this thing as H of G, H delta psi of M. And now I'm suppressing this M of Q thing here because here what is really important is that what is the transformation of the M, the map itself. But remember that M is acting on some Q. Okay, I mean, keep on writing it for transparency, but this is just a way of rewriting these three terms such that we see the HG sort of coming out explicitly. Because HG coming out explicitly is nice. HG is a variable we know how it transforms under different order. And then, okay, it makes sense to just sort of get rid of this half and I will put it 2 here, and forget about this. Because it doesn't matter. At the end of the day, I want this to be 0. So twice of 0 is 0. So now we want to sort of make the following thing, just as we said that it's reasonable to assume that HS does not transform. It is equally reasonable to say that HG transforms exactly as we would expect a self-dual G form to transform on a physical manifold with metric G. Because this is the physical form, and this is the tensor, this is the form. We know how it transforms. So, just to remind you, so the principle is that HG transforms as expected. And just to remind you that any key form this transformation is given by the Patta's formula. Everybody knows this notation or right? It's standard pretty much. And this is precisely true for HG as well, because before it is self-dual, it is a form. So this is something that is true for any differential form. It's sacrosanct, you can't touch this. But for HTP, the fact that it is self-dual means that after we do a diffeomorphism, we have to ensure that it remains self-dual. That's the added piece that comes in when you work with self-dual or anti-self-dual forms. Okay, so you have delta. So I have 1 minus star G acting on HT to be 0. HG is self-dual. Let's take a variation of this. From one side, you will have the variation hitting HG directly, but then you will also have contribution where it's hitting the factor of metric that is sitting in the Hodge group. That means this has to be. This is just a statement that HG is self-dual with respect to G. Just to a variation of that. The variation is going to hit this, but it's also going to hit this. And that means that there is some linear combination of this two variation which has to vanish, and I put it as an equality. This is true for self-dual forms in any cosmetic. Nothing to do with this formalism or that formalism. Nothing. It's just a simple statement. So let's solve this equation something. It's A because we're going to need it again and again.
Can I ask something?
Yeah.
Should I think about this equation like a restriction on the possible metrics G you can have? Or
No, it's basically telling you that how. So okay, typically when you talk about diffeomorphism properties of the forms, the metric is not important. Like look at this thing, right?
yeah.
It could be any metric as long as it's a compatible metric that you can define on the manifold. It works out, right? But then the fact that this is self-dual means that there has to be something more information about the metric that has to enter into the transformation property. Because it's not just a differential form, it's a self-dual differential form. Self-duality is a condition that is defined with respect to the metric itself.
So it's a restriction on how HG can transform.
Exactly. Okay. this out. But on the other hand, remember, we had this expression that you could write Q in terms of HT as P plus half 1 plus star HT. Q equals to half 1 plus star HT, the equation that we wrote down. So maybe you will remember this. Wait. Now that means if I take delta psi of Q, I'm going to have this star is not going to talk to the different office because this is the star with respect to India. Okay. So this is another equation. And finally, remember HT is given by the small n of Q, by explicitly Q minus capital N of Q. Now, if I take a variation of this on both sides, I have just took a variation on both sides. This one is going to eat on Q and then I will do this.
Right, why isn't there a variation of the last Q?
Yeah, there is a variation of the last term as well. So there is a name of letter Q. And what I can do is that I can take and this and just simply write it as n of delta Q. Yeah. Now, if we take this and substitute it here, there is a delta z hg on the right hand side. Take this and substitute it here. 1 minus star g is going to kill this one because small n is a map which takes eta cell dual and maps to G cell. So 1 minus star G, when it acts on this, is going to kill it. The other term is going to remain. So this will give me the negative sign. Okay. So this A times. So it's just A will simplify using that. Now what we are going to do is that definitely it will be good to keep on working on this code because I want to keep on simplifying this. I can use this, right? Everybody knows this and knows this. So this one, let's keep it as it is for the time being. This one, I'm going to write it. Does this make sense? Because this is self-dual with respect to G, which means that it's only going to talk to the anti-self-dual part with respect to G's thing only. And so I just replaced, or I just made it explicit, so to speak. Okay. Then what we can do is use this fact that when you have 1 minus star G delta xi m, I can replace it with this with a negative sign. Essentially, let's see. Space. Let's just try to continue from here only. So essentially now at this point, this equation now I'm going to replace with this because this is also true. It's a bit of a convoluted gymnastics because these two equations are really the same, but essentially what we are doing is that we are trading off delta xi of n in terms of delta xi of h, and the intermediary is through delta xi of star g. Okay. So we are going to replace this by that, and you could have just kept 1 minus star g explicit if you want. So star g delta xi. But now you know there is no need to worry about the projection. You can just simply write it like this. Is this manipulation clear? I think
It's a bit weird. You sort of made sure everywhere the variation of subdual form should still be subdual. Now, the only thing radius can be non-zero if it's not subdual.
Yeah, but so the whole point is that now this thing is going to severely constrain that what delta xi p and delta xi q is going to be, right? In fact, it's going to determine delta xi p, and then once that is determined, that will immediately fix what is delta xi q, right? So at this point, I just only manipulated this in such a way such that this expression, which involves how n transform, can be especially written as how Hg transforms. And that is good in a sense because I know how Hg transforms. So that's what I want to get at. So
yeah, but is transformation of Hg subdual G subdual or not G subdual?
So you have to ensure that it is self-dual in the sense that this is what we argue, right? That it has to sort of, and this is a consequence of that, right?
But I would say this term is zero.
You can argue that this term is 0, but I mean we don't want this term to be 0. I mean we just want to manipulate and keep the term 0 in such a way, and then combine with this and then sort of fix what details is like this.
Okay, but then this argument is not quite correct. Is it?
This is just simply taking the. This is just simply sort of taking the transfer. Okay, I understand what the confusion is. You are saying that this thing is self-dual with respect to G. That's not quite correct, right? Once you have the thing with self-dual with respect to G, then the diffeomorphism sort of acts both on the Hodge dual and the transformation itself. This thing is only true if it is working with the flat space. So Q equals to star Q, then delta xi Q is also star of delta xi Q, because the delta xi does not act on the star. But in the curved space, the correct way to do it is essentially this.
Okay, so you're saying there's a difference of taking the variation of H and saying it is self-dual.
Yeah.
And taking the variation of the
Taking the dual and then take the variation.
right.
So this is precisely the statement. And that the difference, as you can see, that this is not 0.
Right.
And the difference is precisely when xi acts on star G. And this tells you that only in the flat space cases it will be 0. Sorry, I could not understand your question initially and I confused you, but this is proving that delta xi is
Okay. So I'm confused about one thing though. So self-dual forms are representations of the Lorentz group.
With not on a curved manifold, that's not true.
No.
On a flat manifold, yes. On a curved manifold, no. Because the self-duality is defined with respect to this non-trivial metric G. And that is not a representation of Lorentz symmetry, Lorentz group, right? And I can do it for any arbitrary metric G. There is a local Lorentz symmetry, of course. I can gauge fix it to express it in terms of BL, YM, etc. There's a local Lorentz symmetry, but that is true for any tensor field on a curved manifold, right? There is a local Lorentz symmetry under which these things transforms nicely. You have to choose a suitable gauge.
Sure.
But globally, they're not something that necessarily furnish a representation of just the Lorentz group. Because these has nice diffeomorphism properties, which is much more than.
So you're saying now if a general diffeomorphism, the self-dual form is not self-dual for
no, it's not. That's what we prove. Precisely because the diffeomorphism will hit on the Hodge dual operation itself. The Hodge dual is in presence of a non-trivial metric, it's a non-trivial operation, depends on the metric. The only thing you can say is this, that this guy is 0, it's a tensor equation, so its variation has to be 0. But then everything else is a consequence.
Yeah, it's a bit strange. I see what you're saying. I understand what you're saying, but
I mean, you think of it like this way: that under diffeomorphism, the forms themselves transform, but so does the metric, and therefore so does the Hodge dual operation.
So okay, let's work in an orthonormal basis with field lines.
Yes.
I can define self-duality with field lines.
Yes.
Is it the same as self-duality without field lines or not?
It is the same, but in the field lines, I can always gauge fix such that this G is precisely beta.
Yeah.
And then this term vanishes, and only in that basis, when I express it, then this thing is going to be true. But I don't have to work in that particular gauge, right? I mean, working in the local Lorentz transformations, I mean, I can work in a general.
Sure, but then. Yeah, I can sort of, but it's like, if you're using spinners, you sort of have to work with them.
Yes, of course,
with
the spinners,
turbines.
yeah, spinners will transform under this thing, but these things don't take value in the spin bundle, right? These are things which are valued in the co-tangent bundle.
Well, that's not so clear, right? You all antisymmetric fields.
You can map them.
Will be written as bispinors. So
Yes, okay, you can map them. You can find a sort of map, and you can map them to corresponding object in the spinor bundle, and in that bundle, this equation will be simpler because I can always locally gauge fix and make the G is basically an eta.
right.
But I don't have to do that, right? I can work
but
on
it somehow should be compatible.
it is compatible. It is compatible. Because the moment I do a gauge fixing where G goes to eta, you see this equation is simply telling us that this H expressed in that basis, G expressed in that basis, is simply 1 minus R delta psi 0.
Right. So then somehow this argument
But I'm here.
works out in a different way.
No, it's not. I'm not working on a local coordinate frame, right?
I know, but you could.
I could, but then this expression would look different.
Maybe this would be zero by itself and you're happy because you wanted to do zero in the end.
I don't want this to be 0 by itself. I want this to determine what
In
is
this
the
case, but the whole thing you want to do zero.
yeah. In some sense, okay. Let me put it this way. Even if you use this local coordinate basis, you will still end up with a sort of. So essentially, the point is that you will end up with some diffeomorphism property of this field strength itself, right? Delta psi H is not going to be 0; it's still going to be given by the Kata formula, right? And that in itself will determine this thing. So there is no incompatibility here, right? I mean, this is a very frame independent way of working with it. It's an expression that is sort of well defined in curve manifold. This you might say that okay, I don't understand what is this or what is this. But when I have reduced it into this form, this is a well defined object on a curve manifold. Right? It's a form and then it's linear derivative with respect to a vector field. And this I understand. This I know how to make sense. And that was the whole goal, that one of them I reduce to this, and then I know how this guy transforms. And then I don't know how this guy transforms, but then I want to demand that this whole thing should be invariant. That fixes what detail does that fix.
Sure. I see where you're going. I'm just trying to.
I mean, if it sort of so in Ashoke's original paper, interactive discography, right, in 2015 paper, he works in the kind of thing that you're talking about. He works in local Lorentz indices. So he gauge fixes. He finds an expression of M in terms of real lines, and he has the things and etc. etc. And even then, you will see that you can find what is the d delta psi p and what is delta psi q, and it's the same expression that we're going to.
But isn't the point then that if you want to do it in this in Vielbein, then we also have to show that it's invariant under local Lorentz transformations?
I mean, so it's going to be manifestly local Lorentz invariant. That is going to be guaranteed because you see this whole structure is something which sort of restricts Lorentz transform.
Yeah, but you're making choices.
But yes, the point is that you have at this to go into local Lorentz frame at some point you have made a great choice.
You should also make like you make changes in diffeomorphism. You should also make changes.
Exactly. So your diffeomorphisms are something that respects that gate choice, which has reduced you to this Lorentz transformation. So in some sense, this is I mean both are equivalent way of doing physics, right? It's just one is just gauge fixing, and another one is that we don't do any gauge fixing. We work in a sort of gauging very directly. Right? But this statement, for example, this has nothing to do with any formalism. This is just a geometric statement of a self-dual or anti-self-dual form field on a manifold with some metric tensor. This is just maths. There is no physics, so to speak. Yeah. Okay, we are fantastically over time. Sorry.
No,
but it is not
the
a.
automatic formula tells how we transform.
Yeah, exactly. So essentially, at this point, I'm going to replace this by the Carter's magic formula, and so let's just simplify this guy. Right? We have and then essentially this is a true statement. I hope it will be. If you have a P form and a 4n plus P minus P form, and if you take its contraction of the first one, you can exchange the order of this. You can take the contraction of the second one and etc. at the cost of a sign. This is in fact there's nothing to do with 4n plus. It could be true for any.
Your ones and twos looks the same.
Sorry.
Your ones and the twos looks the same.
This is one.
This is
This is two. This is one. Yeah. This is a property everybody knows, right? It's because this thing is like it has some like property, right? And the total derivative, it doesn't make sense because that is like 4n plus 3 form in a 4n plus 2 manifold, so that's the event. So then you just have the other terms. And this is true for any odd, but in our case it's particularly true, and then of course P is 4n plus 2n plus 1 here. And essentially what we get is that if you have I psi DHG HT, this one, then write it as I psi HG with DHG using that formula. But this I can write as D of I psi HG with HG plus a boundary term, total derivative, which we are going to know. So this combination, essentially up to a boundary term, reduces this combination. So sorry, this and then it's the same term, so it's twice of this. It's clear? So I'm going to just replace this here. So there's the twice. And then this is D of I psi of H. And now we are essentially done because you see that it's the same thing that is multiplying both of them. You have a D acting on delta psi P and you have a D acting on I psi of HT. I mean, okay, twice. So the simplest way to make sure that this vanishes is simply say that delta psi P is, oh, there's a twice here as well. So no negative. It's so I just took this term here, use the Carter's magic formula, then this second term, I just showed that it's equal to the first term up to a boundary term. So then this whole thing is basically twice the first time. Right? And then there were two twices, and this is the essential thing. And once you have delta psi p, then that determines. So once you have delta psi p, this determines what delta psi q is. So we can just write it down once for completeness sake.
Can you push up the other blackboard?
Yes, that's correct. Is it visible?
Yeah.
So these are my delta psi p's and delta psi q's. Yeah. And you see once again, like we discussed, like it's the presence of that fact that this is star and not star G, which is kind of ruining the fact that Q does not transform like a differential form. Okay, so this is a natural stopping point in terms of formalism. We are essentially done. There's a small calculation that I wanted to show here because that calculation is kind of quite general and it's a natural thing to do at this point, which is precisely that now that we have figured out how to couple to gravity and make the theory general coordinate transformation invariant, what's the stress tensor of this theory, right? And so essentially, I mean, if you want to calculate the stress tensor, it's the same definition, you vary with respect to the metric, the action. This doesn't contribute, this doesn't contribute. The only contribution comes from this. And the only thing that contributes in that is that when M, the map itself is varied with respect to metric, because everything else is completely unaware of the metric. The measure also in this. And then when you do that, it's a very straightforward computation that you can compute using the map M that we have given and etc. Right? And then you get a very sort of nice result. The result that you get is that the T mu that you compute using Sen has a very nice interpretation. Is that this is precisely the T mu that you would compute from a minimally coupled Maxwell-like action for a generic form, not self-dual, anti-self-dual, anything. But then you impose this. So this Maxwell action that I'm talking about is basically cleavage star G with G, and this is integrated over the physical manifold. And this has to be the case because the on-shell stress tensor is something that you can already compute from the pseudo action. Because remember, pseudo action is not a well-defined thing off-shell, but at the level of equations of motion is perfectly fine. It gives you the correct equations of motion, which means that the on-shell stress tensor that you compute from here is a well-defined meaningful quantity. So whatever new formalism that you give, which gives you a new way of doing off-shell physics, on the on-shell it has to agree. Sorry. And here we are essentially proving it. And if you remember in the first lecture, I told you that this is precisely one of the assumptions made by Witten and Alvarez-Gong in the seminal paper where they computed the gravitational anomalies. They could not derive the Feynman rules because they didn't have an action for the self-dual formulas. But they made two assumptions. They put out the fact that the propagator should be the propagator of the field strengths, and the vortices where the graviton is coupling to the stress tensor. They said that the stress tensor we compute using the Maxwell action, and then we project out the anti-self-dual part. That gives some stress tensor. And let's use that as a Hertz factor. So we are already seeing that the same formalism is reproducing that vertex factor, and in fact, it also gives you the current propagator. But now you can derive it from first principle. You don't have to postulate it. And this is, we know that this is a correct thing, right? Because gravitational anomaly of type 2B cancellation that crucially hinges on this particular contribution to the anomaly. So whatever new formalism somebody proposes, they have to reproduce this one anomaly computation. Right.
So.
Yeah.
The computation of the stress and transfer. So, I mean, the metric is hidden somewhere. So, what do I do? I make a translation using these transformations.
Yes.
And check the conserved current.
So the metric is hidden precisely in this end.
Yeah.
And you can evaluate this distance in two ways. One is that you can directly define it the standard way. Right.
Okay, so you need to find M, how M is.
You don't need to do that. The construction that you give here,
Yeah.
you can explicitly prove that for any G, that M is such that the delta M, delta G mu is precisely going to give you a stress tensor which will have this interpretation.
But I guess the T Sen is given by that formula up there, right?
Well, so that's what I'm asking. Can you do the differentiation?
It's the same definition of the stress tensor.
Yeah.
Definition of the stress tensor.
This definition, by the way, called the Hilbert metric stress energy momentum tensor.
Yeah. This is the same action. When you evaluate it in same action is that, and then when you evaluate Maxwell action.
But isn't that more or less clear? Because you said that that's the only place where G enters and so on.
Well, so what I'm asking is.
But I mean, the fact that this formula is true, of course, it's clear. But I'm saying that the fact that this formula has an interpretation like this.
Yeah, that's the non-trivial. Yeah,
but that's the non-trivial.
Yeah,
that's the non-trivial state.
Yeah,
What
I was worried about was whether you made a difference between T Sen and T Hill.
No. It just means that it's evaluated for sense action.
Yeah.
This formula.
You haven't asked my question. So can I do? I mean, another way of defining stress tensor is I do a diffeomorphism.
Yeah.
And check for the conserved current.
Yeah, it's the same.
And I get the same thing. It works with these transformations that you have to do.
Yeah, same. So I was about to say that of course, I mean, as in any theory, you can compute the stress tensor in two different ways.
Yeah, but it's not here. It's not here.
Of course. Yeah. So that's why. So this was first put out in the paper by I erased that in Angiolo, Lambert, Kopaciosikis, but actually independently at that time we were also writing a paper and we kind of knew that, but they sort of scooped us at least in that particular result. We were interested in doing TT bar deformation, so for us this was important, right? To know how to stress, what is the response to this on the stress tensor and everything, and I mean, this is a very nice fact because if you want to compute the stress tensor, you don't have to work with this thing. There's a shortcut. You can just quickly do it, and it's a very nice thing to do. Yeah, it's a
tangential question. So you mentioned in the first lecture that whatever you do for self-driven fields, you can do the same for a 4-inch space, manifold, and let's say the replace self-driven, anti-self-driven, and all of this will follow, which is going to be true. Is it the same at this point?
Yeah, it is still true. The only thing will change is that in 4N, you will have to work with imaginary or anti-imaginary self-driven if you still want to sort of in Lorentzian spacetime. If you're in Euclidean spacetime, then you can just work with self-driven and anti-self-driven really.
Okay.
So the counting, the way it goes is that the signature is important as well as the dimensions. So that's the counting I did in the very first lecture first. So 4N plus 2 Lorentzian real forms are self-dual and anti-self-dual. 4N Euclideans are real self-dual or real anti-self. If you're in 4N Lorentzian, then you have to work with imaginary self-dual or imaginary anti-self. But yeah, this goes through.
You said there are three ways of computing M, right?
That's true, yeah.
So all of them give the same descent?
So, I don't know about Pichet's thing. As far as I understand, nobody has used that apart from him. But for the sense thing, yes. This was the stress tensor. In fact, for chiral boson, Ashok already computed this, and the way he computed was precisely as Ricard was saying, as a Noether current for the translational symmetry, right? But then once Andrew Low Lambert and of course our paper came out, it became clear that you can also do the standard thing and that gives you the same answer. And I mean, in some sense, it had to, right? Because this is not a stress tensor, it's not a quantity that you can, it's a well-defined quantity answer. We already knew what the answer is going to be. So it's another thing that I want to sort of mention is that you can see here, of course, this coupling to the metric is a very non-standard way, but I like to think of it as like as a minimal light coupling in the sense that it gives you the stress tensor of a minimally coupled pseudo action. But for example, now if you want to think of this coupling to higher derivative gravity, so for example, the stress tensor, if you have something like, say, FR F squared, right? The stress tensor is going to be different. In here, that should reflect in a change of M. So you should find an M which is like this M plus something, which indicates a higher derivative coupling. And this is something, some understanding of this has been put forward in this paper, but this is something that in my mind is not completely clear that how to systematically progress with higher derivative coupling. It's obvious that it can be done, but what is the systematic prescription? Right? Because I don't want to sort of compute for case by case basis. Somebody gives me like this kind of expression, I should know how to reproduce it. So this is a sort of an open problem, and it's a very important problem on the string theory side because we know that this kind of terms are there, like a lot of time connections are there in the string side. So it's something that I like to understand, for example, forward. But sorry, I didn't have time to go through the proof, but if you're interested, you can look into the paper, or I have the notes, you can look into my notes. In fact, because I mentioned that there are 3 different tests, maybe just for once I can just write down the archive number so that you know where to look for what. So the original paper which started everything is Ashoke Sen. This construction in itself is not hard to understand, but part of the motivation comes from structures and string physics. So if you kind of know that physics, it is a little simpler, but otherwise it's kind of, it could be understood on its isolation. Okay. But this is the original paper which started everything. And this paper specifically discusses type 2 supergravity, but all of the discussion can be generalized. It's on special to type 2 supergravity. And then the paper that I mentioned earlier is Andrew Lambert and Georgikis, and this was extended by Charles. This. So this is the second approach. The third approach is by PV. This one, but PV and his students also kind of had a paper on this approach. Particularly, they showed that the Hamiltonian factorization still works in even if you have if you replace by eta by some G bar and stuff like that. But I mean, foundational paper I would say is that like this and this two. So today's lecture I focus mostly on this one. And I talked briefly about some results from this.